Timer left.
Would you like a cup of coffee?
Yeah, sure.
Okay.
Oh my god, the cup is so hot.
Oh my god, put it here, put it here! Is that It was okay. So,
Oh my god, where did the coffee go?
Oh no! I'm so sorry, Paul.
Oh.
See you later.
See you later. So, how did the styrofoam cup dissolve? To understand that, we first need to go over what it means for something to dissolve. The process we know as dissolution actually occurs in 3 steps. First, expanding the solute, then expanding the solvent, finally combining the solute and the solvent. Now you may ask, what does it mean to expand something? Essentially, expanding a solute or solvent means to move the particles away from each other so that they may combine in the 3rd step of dissolution. So, whether something dissolves depends on 3 key factors. First, how easy is it to separate the solvent particles? Second, how easy it is to separate the solute particles? And third, how much are the solute and solvent particles attracted to each other? Each of these factors depend on the strength of the intermolecular forces between the particles, which in turn is dependent on the polarity of the molecules. The bowl we used in the video actually had a molecule called acetone in it, or by its official name, 2-propanone. As you can see, acetone is a fairly symmetrical molecule, and despite the oxygen making it slightly polar, acetone generally acts as a nonpolar molecule due to its relatively even charge distribution and low bond polarity. This means that acetone molecules have relatively low attraction to each other. This means that the expansion of acetone is only slightly endothermic, meaning it requires only a little bit of energy. Something similar is true for styrofoam, also known as polystyrene. Although there are strong London dispersion forces between styrofoam molecules due to its high number of electrons, the molecule is nonpolar, which means there are no dipole-dipole forces, causing the molecules to have very little attraction for each other. It is true that styrofoam and acetone do not exhibit terribly strong forces on each other. However, since there are so many more sites for the solute-solvent interactions, this attractive force is more than enough to overcome the solute-solute interactions and the solvent-solvent interactions, both of which are very weak. This would not have been the case if we tried to use a polar solvent such as water, as the attractive forces between the solvent particles would have been much too strong to have been overcome by the solute-solvent interactions. This is especially the case in water due to the strong hydrogen bonding forces. This understanding of dissolution isn't entirely accurate. Technically, whether something dissolves isn't just decided by whether the process is endothermic or exothermic, also known as the enthalpy of dissolution. Some spontaneous dissolution reactions are endothermic due to the increase in entropy associated with dissolution. In reality, both factors play a role in whether dissolution is spontaneous or not, as shown in the equation below. Despite this, the enthalpy of the dissolution process is still an excellent indicator of whether dissolution is thermodynamically favored.
Hey Healy, Paul's walking through the desert right now.
Oh, he is?
Yeah, and when he comes back, he's gonna be so thirsty.
You know, I have a magic trick just for this. He's gonna pour his water in the cup, right? And then once he looks at his cup, there's gonna be nothing there.
Really?
Yeah.
That's so good.
Let's do it right now.
Let's go.
Sodium Paul a thirst. Sodium Paul a thirst. Sodium Paul a thirst. Let's go.
Oh my god, I'm so parched. That desert was so hot. Oh my god, finally some water here. Oh my, why does everything I need keep disappearing? So what happened here? The cup that we poured the water in actually had a powder called sodium polyactylate in it. When this chemical makes contact with water, it traps the water molecules with strong hydrogen bonds between the oxygen of the sodium polyactylate and the hydrogens of the water molecules. This causes the water to seemingly disappear as it was absorbed by the sodium polyactylate. Fun fact, this chemical is also used in diapers since it's very effective at absorbing water. You probably already know this as the elephant toothpaste experiment. The reaction that occurs is actually the decomposition of hydrogen peroxide. If this is true, why does the reaction only seem to start when potassium iodide is added, even though it's nowhere to be found in this reaction? Actually, the reaction does occur before the potassium iodine is added, just very slowly. The potassium iodine acts as a catalyst, meaning it speeds up the reaction. So how does it do this? The uncatalyzed reaction has a very high activation energy, which means that it takes a lot of energy for the reaction to occur. This causes the reaction rate to be very slow. Now let's take a look at the reaction when a catalyst is added. Notice that the iodide ions from the potassium iodide appear both on the reactant side of the first reaction as well as on the product side of the second reaction. This means that iodine is both used up and produced, so it will not appear in the overall reaction. However, the presence of the iodide ions allows the reaction to occur according to the mechanism shown above. This new mechanism allows the reaction to occur with a lower activation energy and therefore have a faster reaction rate. So how did they do this without burning themselves? The mixture they soaked their hand in was a roughly 1-to-1 combination of butane and water. The butane combusted, but the water was able to absorb all the heat that would have been transferred to hand, preventing the person from getting burned.